Welcome back to the deep dive.
Mm.
Today,
Aw.
we are going underground, and I don't mean just digging a hole in the backyard.
Yeah, we are talking about the absolute belly of the beast here.
Massive, ancient chambers of molten rock deep in the Earth's crust.
It is a completely alien world down there. I mean, we are talking about conditions of heat and pressure that are really hard to even visualize.
Right, and the reason we're going there is to figure out where the world's stash of critical metals actually comes from.
The good stuff.
Exactly. We're talking about nickel, copper, and the platinum group elements.
The stuff in your electric vehicle, your phone, the ring on your finger.
Yep, and I've got a stack of notes here ranging from mantle geochemistry to comparative planetary science. And the mission today is to unpack this specific geological phenomenon called layered intrusions.
Right, and to be clear right up front, we aren't just talking about mining in the general sense.
Oh, no.
We are looking at what I like to call magmatic plumbing.
Magmatic plumbing. I actually really love that image.
Well, it fits, right? Because we aren't just looking at static rocks, we are looking at the frozen remains of liquid magma evolution.
Right.
So imagine a massive cavern in the crust, sometimes hundreds of kilometers across, filled with magma, cooling down incredibly slowly over thousands or even millions of years.
And because it cools so slowly, it allows for some extreme physics and chemistry to take place.
That is the crux of it. If you just flash froze that magma, the metals would be scattered everywhere.
Just background noise.
Exactly. You'd never get them out economically. You need the plumbing system to sort them.
Well, so let's start with the structure itself, the layer cake.
Mhm.
I found this fascinating because the sources mention that this isn't just an Earth thing.
No, not at all.
There was this specific reference to the moon in one of the papers, which really caught me off guard.
Oh yeah, the lunar connection. It's a great connection to make. The source actually discusses the Mg suite, or magnesium suite, of rocks on the moon.
Wait, so hang on. We have layered intrusions on the moon.
You do?
That is wild.
Yeah, the current thinking is that after the lunar magma ocean, the literal ocean of lava that covered the early moon.
Right, when it was just a glowing ball.
Exactly. After that crystallized, there were these pockets of magma that intruded into the lunar crust, and they cooled slowly, just like on Earth, forming these layered magnesium-rich rocks.
So it validates that the physics we are discussing isn't just a local Earth quirk.
Right. Gravity works the same way up there. It's a universal planetary process.
Okay, so walk me through the mechanics of that. We have this giant vat of magma. It starts to cool. Why do we get layers instead of just a big solid block of gray rock?
Think of it like sediment settling in a lake. If you dump a bucket of sand and mud into a lake, the heavy sand hits the bottom first.
And then the silt, then the mud.
Precisely. In a magma chamber, you have crystals forming in the liquid.
Crystals of what exactly?
Minerals like olivine or pyroxene. As the magma cools, it hits these specific temperatures, what we call catectic points.
Catectic. Yeah, that word came up a few times in the technical papers. Define that for us.
Sure, a catectic point is basically a sweet spot in temperature and pressure where multiple minerals become stable simultaneously.
Okay.
So suddenly, the magma just starts crystallizing these minerals in droves. And because these crystals are denser than the liquid magma,
They think.
they sink. They settle at the bottom of the chamber, forming a distinct layer.
So it's literally raining crystals inside the magma chamber.
Raining crystals, yes. Then, as those minerals are pulled out of the melt, the chemistry of the remaining liquid changes.
Because you've subtracted certain elements to make those crystals.
Exactly. It evolves. So it might reach a new catectic point, start forming a completely different mineral, and lay down a new, differently colored layer on top of the first one.
Like a salad dressing separating in the fridge, but it happens in stages over millions of years.
That is a very fair analogy, and this layering can be incredibly precise.
How precise?
Well, in the Bushveld complex in South Africa, which is sort of the undisputed king of these deposits, you can trace single layers of rock for hundreds of kilometers.
Just one unbroken layer.
Yes, it's that consistent.
Wow. Which brings us to the money,
Yeah.
right? Because we aren't mining these things for olivine or pyroxene. We want nickel, copper, platinum. But these are rare metals.
Yeah.
Even in a big magma chamber, they're just trace elements. How do they actually get gathered up?
This is where the story gets really interesting. In a normal silicate magma, just regular molten rock, these metals are very dispersed.
Oh.
They are actually locked inside the silicate structure in tiny, tiny amounts. To get a mineable reef, you need a collector.
Something to sweep through the magma and grab them.
Exactly. And that collector is sulfur.
sulfur, okay, which
Mhm.
introduces this concept of sulfide immiscibility.
Right.
And immiscibility just means they don't mix, right? Like oil and water.
Precisely. Imagine your magma chamber is a huge pot of hot water. That's the silicate melt. Now, you introduce sulfur.
Okay.
When the conditions are right, usually when the magma cools to a certain point or there's a certain chemical interaction, it becomes saturated with sulfur.
It can't hold anymore.
Right. So suddenly, little droplets of sulfide liquid form.
So now we have droplets of liquid sulfide floating around inside the liquid rock.
And because they are immiscible, they stay separate. But here is the magic trick. The metals we care about, the nickel, copper, platinum, palladium, they are chalcophile.
Chalcophile. I looked that up. It means sulfur-loving.
Yes. They hate being in the silicate magma, but they absolutely love being in the sulfide.
Oh, I see.
So as these little sulfide droplets float through the magma, they act like a sponge. They aggressively strip the metal atoms out of the surrounding liquid.
So the sulfide droplet is basically swimming around eating all the platinum and nickel it can find.
It's scavenging, and the efficiency of this scavenging is determined by something called the R factor.
Yes, the R factor. That was highlighted heavily in the sources. It sounded like a math equation in the text, but it seemed crucial. Break it down for us.
It is math, but the concept is very simple. R is just the ratio of the amount of silicate magma to the amount of sulfide liquid. Think about it this way. If you have a huge swimming pool of magma with a tiny amount of platinum dissolved in it, and you drop in one tiny sponge,
That sponge is going to get soaked.
it's going to get incredibly saturated with platinum. That is a high R factor, a huge volume of magma interacting with a very small amount of sulfide.
And that creates a very high-grade ore.
Extremely high grade.
Conversely, if I dump 1,000 sponges into the same pool,
Each sponge only picks up a tiny bit of platinum. You've diluted the resource.
that's a low R factor.
Exactly. So economically, we are looking for geological settings where the R factor was high, where nature ran a very efficient scavenging operation.
Okay, so we have these supercharged sulfide droplets. They're heavy, so they sink to the bottom, forming what the miners call a reef.
Correct.
But the sources mentioned something that completely blew my mind about this. The offset reef model.
Ah, yes. The Neldrit and Wilson model. This is where we see just how organized nature really is.
Because it's not just a big jumble of metals in that layer, right?
Mhm.
The text seemed to imply there is a strict hierarchy.
There is a very strict vertical sequence. It all comes down to partition coefficients.
Which is a fancy scientific way of saying, how badly does the metal want to be in the sulfide?
That's exactly it. And the platinum group elements, the PGEs, have the highest partition coefficients.
They're the hungriest for it.
The hungriest. So imagine a batch of sulfide droplets forming. The moment they appear, the PGEs jump in first.
Like the first people rushing a buffet.
Great analogy. So the very first sulfides to settle out at the absolute bottom of the layer are intensely rich in platinum and palladium.
But once they settle, they've stripped the local magma of all its PGEs. The PGEs are gone.
Right. So what happens to the sulfide droplets forming, say, 5 minutes later?
Well, the platinum's gone, so they have to grab the next best thing.
Which is gold. Gold has a slightly lower partition coefficient, so just above the platinum layer, you predictably find a peak in gold.
And then,
Finally, copper. Copper wants to be in the sulfide, but not as badly as the others, so it gets concentrated last, forming a layer at the very top.
so if I'm drilling down into one of these reefs, I should theoretically hit copper first, then gold, then platinum at the very bottom.
Ideally, yes. That is the offset reef pattern. PGEs, then gold, then copper, moving upwards.
That is amazing.
The money intrusion in Australia is the classic example cited in the text where this sequence was really perfectly documented.
It's incredible that you can predict where the gold is relative to the copper based on cooling physics from 2 billion years ago.
It is elegant. However, science is rarely that tidy.
I sensed a but coming. The reading mentioned a researcher named Barnes who kind of threw a wrench in the gears.
He did. Barnes and others have pointed out that while the offset model is a great general rule, the math doesn't always add up perfectly in reality.
How so?
Well, if you just use the simple partition coefficients we measure in the laboratory, the actual rocks sometimes show different concentrations than we'd expect.
So the offset model is wrong.
Not wrong, just incomplete. Barnes suggested that we might be missing a step in the process.
What kind of step?
Maybe the metals aren't just dissolving into the sulfide liquid. Maybe they are forming tiny little nuggets of metal alloy before the sulfide even forms.
Oh, like preforming chunks.
Right. Or maybe the way the sulfide liquid itself crystallizes later on changes the final distribution.
So there's a legitimate debate happening.
A very healthy one. It implies there might be other phases or materials involved that we haven't fully characterized yet.
It's a good reminder that even rock-hard geology is still an active field of discovery.
Absolutely.
I want to pivot slightly here. We've been talking a lot about the shiny stuff, the sulfides.
Yes.
But looking at the cross-sections in the show notes, there are these other massive dark layers in the intrusions, the oxides.
You definitely cannot ignore the oxides. In these same intrusions, you often find massive layers of chromatite, which gives us chromium for stainless steel, and magnetite, which is iron ore.
Do these form the same way, like droplets settling out of the magma?
Not exactly. Sulfides form because of immiscibility, like we discussed, but chromite layers often form due to magma mixing.
Mixing of what with what?
Two entirely different types of magma. Imagine the chamber is effectively full and cooling down nicely.
Okay.
Then, suddenly, a fresh pulse of hot, primitive magma injects into it from below.
A shock to the system.
A massive chemical shock. When those two chemically distinct magmas mix, or sometimes if the magma melts some of the surrounding silica-rich wall rock, it pushes the chemistry into a specific zone.
A zone where what happens?
A zone where the only thing that can possibly stabilize is chromite.
So it suddenly dumps all its chromium at once.
Exactly. It just rains chromite crystals, forming these incredibly dense black layers. Sometimes they're meters and meters thick.
Wow.
And then you have the magnetite, the iron layers. Those usually happen higher up in the stratigraphic stack.
The notes mention something really wild about the magnetite layers. Ultramafic pegmatites.
Ah, yes. That is a fascinating theory.
Because pegmatite usually implies big, chunky crystals, right?
Usually, yes. But here we are talking about fluid dynamics inside the rock pile. The theory is that as the crystal pile builds up at the bottom of the chamber, you get these dense, iron-rich, residual melts trapped inside it.
The leftovers.
The heavy leftovers. And they literally drain downwards.
Like water percolating through sand.
Yes, but imagine the water is heavy, iron-rich, molten rock, and the sand is a pile of hot crystals.
That sounds intense.
It drains down, physically cutting across the horizontal layers, forming these discordant pipes of iron-rich rock.
It really reinforces that magmatic plumbing analogy you started with. It's not just a static bucket of rock.
Not at all.
It's draining, it's mixing, injecting new material.
It's a highly dynamic, evolving system. And really, that brings us to the consequences of us coming along and poking holes in that system.
Right, because eventually we find these things, we dig these sulfides up and bring them to the surface.
We do.
And according to the sources, specifically source V11, that is where the chemistry turns against us.
It does. This is the big environmental hangover of mining sulfides.
Walk us through it.
Well, the minerals we're talking about, things like pyrrhotite and pentlandite, they are perfectly stable, deep underground, where there is absolutely no oxygen.
Right, they've been sitting there for a billion years.
Exactly. But when you mine them, crush them up, and expose them to air and water on the surface, they become highly unstable. They rapidly oxidize.
And that oxidation releases what?
Acid. Sulfuric acid, effectively. The chemical reaction releases hydrogen ions and sulfate. This is the root cause of the infamous acid mine drainage, or AMD.
I've seen photos of this. Screams near old abandoned mines turning completely bright orange.
Yeah, the orange is usually iron precipitating out of the water, which is ugly, but the invisible killer is the acidity itself.
Because the acid dissolves other things.
Exactly. The acid acts as a powerful solvent. It dissolves other heavy metals locked in the waste rock, lead, arsenic, cadmium.
So you don't just get acid water, you get a toxic cocktail of heavy metals entering the groundwater system.
It's a massive problem. And the source also mentioned a biological component to this that makes it even worse. Bacteria.
Yes, Acidotheobacillus. It honestly sounds like a movie villain.
It is a microscopic villain in this context. These bacteria actually feed on the sulfur and iron.
They eat the rock.
They use the oxidation reaction to get energy, and by doing so, they act as a biological catalyst. They can speed up the production of acid by orders of magnitude compared to just sterile chemical weathering.
So the bacteria are basically supercharging the pollution.
Exactly. They are accelerating the breakdown of the rock to feed themselves, but the byproduct is massive, massive amounts of acid.
And the sources mention secondary minerals too, right? Like jarosite.
Right. The system forms secondary sulfate minerals, which temporarily store that acidity in those metals, but they act like ticking time bombs. If they dissolve later, they release it all back into the environment.
It's a complete cycle, isn't it? We start with magma oceans on the moon, go down to sulfide sponges soaking up platinum deep in the earth, and end up with microscopic bacteria eating the remains of that rock on the surface.
It really highlights why you can't just be a miner anymore.
What do you mean?
You have to be a geochemist. If you know you are mining a sulfide reef, you have to plan for that acid potential from day one. You can't just treat the waste rock like inert dirt because it is chemically and biologically active.
It's a heavy responsibility. But, and this is the core paradox that sources point out, we absolutely need these metals to solve other environmental problems.
That is the trade-off we face today. We are digging up these ancient sulfide layers to get platinum and palladium. Why?
Catalytic converters.
Exactly. They are the primary catalysts that scrub pollutants from car exhaust.
And hydrogen fuel cells, right?
Essential for green energy transition. We need them.
So we are creating a localized environmental risk, the acid mine drainage, to solve a global environmental problem, air pollution, and climate change.
It is a very delicate balance, but understanding the geology deeply is what helps us manage that risk better.
Well said. So let's wrap this up. We have covered a lot of ground today, literally.
We certainly have.
We've seen the magma chamber, the layer cake, the sulfide sponge, the acid-eating bacteria. If you had to pin down one thing for the listener to take away from this huge stack of research, what is it?
For me, it's the predictive power of that offset reef model. It is genuinely staggering that we can look at a cooling history from billions of years ago and confidently predict, if I drill here, I'll hit gold. If I drill 10 meters lower, I'll hit platinum.
It feels like reading the Earth's diary.
It does. But I also want to leave you with that lingering doubt from the Barnes paper.
Ah, the missing metals.
Exactly. Think about it. If the partition coefficients say the metals should be in the sulfides, but the math doesn't quite work out perfectly in the real world,
Where else are they?
that's the question. Where else are they hiding? Are there nano nuggets of precious alloy hiding in the waste rock that we are currently throwing away? Are we missing a whole other fundamental mechanism of metal concentration just because we are so heavily focused on the sulfide sponge model?
It suggests that maybe the next big discovery isn't finding a new mine. It's figuring out a new way to look at the rocks we've already dug up.
Entirely possible. We refine our scientific models, and suddenly what was waste becomes the new ore.
That is a fascinating thought. Well, next time you look at a piece of platinum jewelry, or even just start your car, take a second to imagine the massive, churning magma chamber it originally came from.
And the little droplets of sulfide rain?
Exactly. Imagine the droplets of sulfide rain falling through that magma, scavenging those exact atoms just for you.
It certainly gives you a new appreciation for the geology sitting right there in your pocket.
It really does. Thanks for taking us through the plumbing of the planet today.
My pleasure.
And to you listening, thanks for diving deep with us. We'll see you on the next one.